When forces vary, we'll use the integral form of work to calculate work. That means that work is the integral of F dot dr. Here, with just an x position, we can simplify that for one-dimensional motion and say we can integrate from my initial x to my final x of f as a function of x with respect to x. Graphically, what that means is you can add up the area under the curve as you move along from position 1 to position 2. And you do that by defining an integral element here and figuring out the area of that integral element and then adding up the area of all the different integral elements as you go along. So you can do that in a discrete way by actually numerically integrating, or you can do it in a continuous way by specifying a function here and evaluating that integral. Here we have another example of a function of a force that depends on position, and we can add up the areas the same way. I'm using this one to show you that if you have your curve above the x-axis, that contributes positive work. And if you have your curve below the x-axis, as you add up that area, that ends up giving you a negative contribution to the integral, or negative work. Let's think about the work done by a spring then. So if we have a spring, we already know that as you try and stretch the spring out, it resists that stretching and tries to pull back. We can consider the work done by a spring as we stretch it from some initial position to some final position from A to B. And we can say that that work done by a spring as we go from A to B is equal to the integral of the force of the spring integrated starting at A going to B. We can plug in our function for the force of a spring, which we know is negative kx. The k is a spring constant. A constant means it doesn't depend on how much we stretch out the spring. So it can come out front of the integral. Now we're left integrating x dx. We add 1 to the exponent and then divide by the result, so we end up with x squared over 2. And then we evaluate that between our limits of our initial position xa and our final position xb. As we do that, we get negative k times xb squared over 2 minus a negative k times xa squared over 2. Rewriting this, we have negative 1/2 k xb squared plus 1/2 k xa squared. This tells us that the work done by a spring as we stretch it from one position to another is equal to negative 1/2 k xb squared minus xa squared. All right. Lovely. For anybody who wants a little calculus aside, that's the rest of this video, just explaining this rule here. Feel free to ignore this if you'd like. So this is what we're doing here is an integration. That's an antiderivative. If you think about the derivative of x squared, we multiply by the exponent and then subtract 1. So we get 2x to the first, or 2x. When we integrate 2x with respect to x, we're going backwards the other way. So you add 1 to the exponent, you end up with x squared, and then you divide by the result, 2. For anybody who's just getting started with integration, hopefully that gives you a tool for integrating some simple relationships here. And there's a whole wealth of additional integrations you can explore by studying integral calculus.